Continuing on physical chemistry, we're beginning chapter 7 now with section 1. Now we're going to talk about one component phase equilibrium. Now remember, mu sub I is the chemical potential of substance I. Mu sub I, the beta, is the chemical potential of substance I in phase beta. Now the chemical potential of substance I in phase beta is equal to the chemical potential of substance I in phase delta. That is our condition for phase equilibrium. For example, let's say we have a container here with solid salt on the bottom and then aqueous salt above it. So at the bottom, or throughout the whole system, we have temperature and pressure constant. And then up here we're saying we have a saturated NaCl solution, which means that the water already holds as much salt as it possibly can. Now the number of phases in the system is 2. This is the aqueous phase, this is our solid phase. Now once the solution is saturated, the quantity of the NCl down here, it doesn't make a difference as far as the concentration up here. You can add a little more salt or take some of the salt out, and the concentration up here will remain the same. So the equilibrium concentration of the sodium chloride aqueous is independent of the mass of each phase. Now remember, X is mole fraction. It looks like an X. It's a Greek letter chi, pronounced chi. But it's okay. So chi of J in the phase alpha is equal to the number of moles of substance J in phase alpha divided by the total number of moles in phase alpha. So remember, alpha here is phase. Chi of substance J alpha, it's intensive. And then of course J is our substances. Now we're going to use lowercase f to be the number of degrees of freedom. In the past this might have been called variance. F is the number of independent intensive variables needed to specify the state of the system. Now examples of independent intensive variables could be temperature or pressure, chi1, chi2, it's mole fraction. But remember, not all mole fractions are independent. If you add up all the mole fractions, they must be equal to 1. Now C is the number of components. This is lowercase c. So we're going to add up all the different components from 1 to C of chi I. So I is the substances. And so in summation notation, we're just saying this is equal to 1. This is the same thing as that right there. And remember, lowercase p is going to be the number of phases. So the total number of intensive variables, we have temperature, that's 1, pressure, that's 1, and then to describe the composition, we have components minus 1, because remember how they have to add up 1, times the number of phases. So that gives us the degrees of freedom. F is equal to 2, temperature and pressure, plus pressure times the number of components minus 1. Now we're going to assume that every component, or chemical species, ion, chemical, whatever, is present in every phase, and we're going to assume there are no chemical reactions occurring yet. So at equilibrium for component J, we have the chemical potential of J in phase alpha is equal to the chemical potential of J in phase beta, which is equal to the chemical potential for substance J in phase delta, etc., for all the phases. Which means they're not actually independent. They're all the same. So if A equals B and B equals C, then we already know that A equals C. So that's why for C components and P phases, the total number of equations is actually the number of components times the number of phases minus 1. Now let's talk about the degrees of freedom then. So we're going to take the number of degrees of freedom. We have that 2 from temperature and pressure. Then we have the now I can't think of it. Phases, number of phases times the number of components minus 1, and we need to because they're not of this assumption that every species is independent, etc. We're going to subtract out the number of components times the number of phases minus 1. So this is the total number of intensive variables up here, and this is the number of equations relations among the intensive variables. So we get, distribute that out, we're going to get F equals 2 plus PC minus P minus CP plus C. So simplifying, we just get the degrees of freedom is equal to the number of components minus the number of phases plus 2. This formula is called the phase rule. This is a very important equation. So let's talk about just pure water liquid. Well, the number of components is 1, it's water. The number of phases is 1, it's liquid. So the degrees of freedom is 1 minus 1 plus 2. That's equal to 2. Now that's assuming that the water doesn't self-ionize or anything. Now, so the independent variables, we're going to just say are temperature and pressure. What else could it be? Now, the phase rule is actually true even if every species is not present in every phase. For example, let's say we have a sucrose, sugar water up here, and just pure sucrose down here. There's no water down here. So we have two components, we have two phases, we have 2 degrees of freedom. So let's show the math here. So we have the degrees of freedom is equal to 2 from temperature and pressure, plus the number of phases times the components minus 1. We're going to subtract out here because of this missing water in the sugar. And then we're going to subtract out the components times pressure minus 1 minus this 1 because of the missing in the sugar. So we're going to distribute that out, and we get the degrees of freedom is equal to 2 plus PC plus P minus 1 minus 1 minus CP plus P plus 1. So these cancel out, and we still end up with the degrees of freedom is equal to the components minus the number of phases plus 2. Now let's talk about the phase rule in systems with reactions. Now we're going to say R is the number of independent chemical reactions. Now remember Hess's law. We're saying that independent reactions, we can't write one as the sum of the others, like we do with Hess's law, applying Hess's law. So we're going to say lowercase a is the number of additional restrictions. These might be electroneutrality if we're dealing with ions or something like that. So we're going to say C independent is the number of independent components. So the number of independent components is going to be the actual number of components minus the number of reactions minus any other restrictions that we might put in place. So we have the degrees of freedom is the number of independent components minus the number of phases plus 2. Now let's talk again about water. We said for water, liquid water, we had 2 degrees of freedom, but we said that's assuming it doesn't dissociate. So what if it does dissociate, or form H plus and OH negative ions and so on? Okay, so we have H2O, liquid, in equilibrium with H plus, aqueous, and OH negative, aqueous. So the number of reactions is 1, there it is. The number of components is 3, are water, H plus ions, and OH negative ions. The number of phases is 1, this is all liquid or aqueous. And the additional restriction is electroneutrality, because I know for a fact that the number of H plus ions has to be the same as the number of OH negative ions, because the overall solution is neutral. It can't have a positive charge or a negative charge on the solution. Now the mole fraction of H plus is equal to the mole fraction of OH negative due to electroneutrality. That's our additional restriction I was telling you about. So usually in most cases you're only going to have A is equal to 1 or 0. Unless you're actually applying an electric force field, then it could get even trickier. So the number of independent components is going to be 3 minus 1 is equal to 1. So degrees of freedom is just going to be 1 minus 1 plus 2 is 2. So what that tells us, though, is that the dissociation of water into the ions, it doesn't change the number of degrees of freedom. That's all for section 1.